All right, so we are going to go over a bunch of different formulas today, and I am going to need your help with your calculators to give me some numbers, just like we would normally do in class. Well, especially now that everything's going to be unproctored, but even if it wasn't, these are not formulas that you need to memorize. Even when you get into pre-calc, these are not formulas that I expect anyone to have memorized. That you'll be provided a formula sheet for some of these. The fundamental identities, those ones you need to know. So here are double angle formulas. A double angle formula we use when the argument is 2 times some angle. You'll notice that there are 3 different formulas for cosine. You decide which one to use just based off of what it is that you're trying to do and which one would be more beneficial to you. And then we have just one for sine and tangent. So in our first example, we want to find the exact value of 2 sine of 22.5 degrees cosine of 22.5 degrees. Anytime I see 2 sine cosine where sine and cosine have the same argument, it sparks in my brain that this is a sine double angle formula. And you'll also notice that 22.5 is half of 45, which is a number that's on our unit circle. So that's a pretty good giveaway that we're going to need to use a double angle formula. In this example, we're actually going like from the right to the left. Since we have 2 sine cosine, we can turn that into sine of 2 times whatever the argument is. So that's going to be sine of 45 degrees, and that's one from our unit circle that we know, square root of 2 over 2. In our next example, we have cosine squared of 105 minus sine squared of 105. So if we take a look at our double angle formulas, we have cosine squared minus sine squared, and notice that 105 is half of 210, and 210 is one of the angles on our unit circle. So we have the right side of our first cosine formula, and again, we're going to be moving to the left side and rewrite this as cosine of 2 times 105, which is cosine of 210. And that's on our unit circle. Let's see which one that is. It's at 30 degrees past 180. So cosine would be negative square root of 3 over 2. Questions at all? All right, let's try one more. This time it's tangent. And again, you'll notice that what we're given is the right side of our double angle formula. So this will simply turn into tangent of 2 times pi over 8, which is pi over 4. And tangent of pi over 4, that's going to be square root of 2 over 2 over square root of 2 over 2, which is just 1. It isn't that you're always going in the right to left direction with these formulas. It just depends on what you're given. So although you don't need to memorize these formulas, you do need to be familiar with them so you can recognize when to use them off your formula sheet. Next, we have our sum to product formulas. We use this when we want to transform a sum of sines and cosines or a difference into a product. Right now, we're really just practicing how to use these formulas. When we get into calculus or even in solving equations later in this course, we'll see where this is beneficial. But right now, we really are kind of just practicing our ability to use the formulas and plug in. So if it seems a little trivial right now, it kind of is, but we'll use them for other implications later. So our directions are to express as a product. We have sine of 3x over 2 plus sine of x over 2. So I'm adding two signs together, which is the left side of our first formula. The 3x over 2 is our alpha, the x over 2 is our beta. Now we're going to plug it into the right side of our formula and clean it up. We get 2 sine of 3x over 2 plus x over 2 all over 2 cosine of 3x over 2 minus x over 2 all over 2. And then we simplify our arguments. So with the sine, we have 3x over 2 plus 1x over 2 gives us 4x over 2. And 4x over 2 simplifies to be 2x, but we still have that over 2, like in the big denominator. And with our cosine, 3x over 2 minus 1x over 2 gives us 2x over 2, which is just x. And then we still have that denominator of 2. And we can simplify our sine argument one more time. Those 2's cancel out. We're left with 2 sine of x cosine of x over 2. Questions on that example? In our next example, we're adding two cosines together. So we'll be using our top right formula, where 4x is our alpha and 2x is our beta. We get 2 cosine of 4x plus 2x over 2 cosine of 4x minus 2x over 2. 4x plus 2x is 6x over 2. 4x minus 2x is a 2x over 2. And we simplify our arguments one more time. 2 cosine of 3x cosine of x. Questions, anybody? All right, well, why don't you guys try the next two? So we get the answers of a negative square root of 2 over 2 and 2 sine of 3x cosine of 8x. Let's talk about the first one. Did anybody have any trouble getting negative square root of 2 over 2?
I got to the where it says the 45 and the 30. So are you putting in, where are you getting the square root of 2 over 2 from? The unit circle value that
You got it.
corresponds to 45?
You
Okay.
got it. Since we know exactly what sine of 45 is, we want to pull that value from the unit circle. And same thing with the sine of 30 degrees. We want to actually evaluate it. Because if we can get down to numbers, we want to get down to numbers.
Okay. And that's because we want the exact value, right?
Correct.
Okay.
Anybody, any questions on getting 2 sine of 3x cosine of 8x? I do want to mention with these formulas where we're adding and subtracting different arguments, sometimes you end up with a negative inside your argument, like here or here. If that happens, you do need to use your negative angle identity that says like sine of negative theta is equal to negative sine of theta, and cosine of negative theta is equal to cosine of theta. So if when you're adding or subtracting, I guess it's going to be subtracting, if you get a negative, be sure to simplify it one step further using that negative angle identity. Anybody questions on sum to product?
Do an example of a problem that has a negative angle in
I
it?
think that's going to pop up in these next ones.
Okay.
So here we have our product to sum formulas. Again, just a different formula. You'll see this formula two different ways, sometimes with that 1/2 out in front, sometimes you'll see it all over 2. So if you Google it or open a book or MyMathLab, it might be listed a different way. So just heads up on that. It is the same formula. I typically like the 1/2 out in front, but it doesn't matter. So we're going to express as a sum or difference. We have sine times sine. So that's going to be our first formula right here, where 8x is our alpha and 4x is our beta. Plugging in, we're going to get 1/2 times the quantity cosine of 8x minus 4x minus cosine of 8x plus 4x 1/2 times cosine of 4x minus cosine of 12x. And then the last thing we need to do is simply distribute the 1/2. Or you could put it all over 2. And there we go. Questions at all? Next, we want to write cosine of 9x, cosine of 2x as a sum or difference. We have cosine times cosine, our top right formula, where 9x is our alpha and 2x is our beta. We'll have 1/2 times the quantity cosine of 9x minus 2x plus cosine of 9x plus 2x. And then we clean up. 1/2 cosine of 7x plus cosine of 11x, and then distribute your 1/2. Questions, anybody? Next, we have a cosine 5x over 2 times sine of x over 2. So we have cosine times sine. That means we're going to use our bottom right formula, alpha and beta. I'll have 1/2 times the quantity sine of 5x over 2 plus x over 2 minus sine of 5x over 2 minus x over 2. Simplifying our arguments, 5x over 2 plus 1x over 2 gives us 6x over 2, which is 3x. And then 5x over 2 minus 1x over 2 gives us 4x over 2, which is 2x. And lastly, we'll distribute our 1/2. Any questions? Yeah, I know it's pretty monotonous, kind of plug and chug, but like I said, we're really just seeing how to use these formulas so we can do something with it later. Trigonometry is just a totally new branch of math, so it's kind of like we're starting at the ground level and just learning super, super basic skills so that we can then apply them in subsequent courses. All right, last one, we got a sine times cosine. So we're using our bottom left formula. This will be 1/2 times the quantity sine of 2x plus 3x plus sine of 2x minus 3x. Simplifying our arguments, 1/2 times the quantity sine of 5x plus, well, we're going to have here sine of negative x. So here's where we're going to have to use our negative angle identity. Recall that sine of negative theta is equal to negative sine of theta. We're going to replace that with minus sine of x. And then we'll distribute our 1/2. We get 1/2 sine of 5x minus 1/2 sine of x. Questions, anybody? Anybody just need some more time? It's hard. I'm trying to pace correctly, but without seeing you right, I'm not sure if I'm pacing it correctly.
Could I just have a few more seconds?
Yep.
All right, I'm good, Mrs. Kraft.
All right. Next up, two more types of formulas, half angle formulas and power reducing formulas. I think I probably use the half angle formulas the most. Half angles and the double angles, I actually think the cleanup's a lot easier than a lot of the other formulas. So if I have the option to choose, I'm usually choosing half angle and double angle formulas. All right, so here are half angle formulas. Yeah, I know, gross with the square root. Tangent doesn't, tangent has 3 options. So usually, unless there's a real reason that the square root would be appealing, I choose one of these two for tangent rather than the square root ones. And usually I choose this one because a denominator with a single term is usually easier to deal with algebraically than a denominator with multiple terms. But you can choose any of the 3 for tangent. You'll notice that the ones with the square roots have a plus or minus in front of it. This does not mean that there are 2 answers for every single problem. This means that it could be positive or it could be negative, and you need to figure out which quadrant the original angle, the angle in question, is located in, and then determine whether sine or cosine would be positive or negative in that corresponding quadrant. So let's find the exact value of sine of 7 pi over 12. We let off this giant formula section with like sum or difference formulas, and we could use a sum or difference formula to find this. I just think it's a lot more work. If you double the denominator of what you have, if you end up with something that's on the unit circle, then you know that a half angle formula is applicable. This is the same as sine of 7 pi over 6 divided by 2. And 7 pi over 6 is on our unit circle. So this 7 pi over 6 is going to be the alpha that we're plugging into our formula. We need to determine whether sine is positive or negative at 7 pi over 12, so we can determine whether we're using the plus or minus from the formula. So just think about where that angle is. What quadrant would that be in? Well, 6 pi over 12 is the same as pi over 2. So this is a little bit more than pi over 2, which means that we have to be in the second quadrant. Is sine positive or negative in the second quadrant? It's positive. So we're going to use the plus. All right, we get plus, and of course you don't have to write the plus, plus the square root of 1 minus cosine of 7 pi over 6 all over 2. And now we clean up. 7 pi over 6 is on our unit circle, so now we just need to find that cosine value. That's pi over 6 past pi, a 30-degree reference angle. Cosine is negative square root of 3 over 2. This becomes the square root of 1 minus a negative square root of 3 over 2 all over 2. We'll turn this into the square root of 1 plus the square root of 3 over 2 all over 2. You'll notice that we have a complex fraction underneath of a radical. We don't really like a complex fraction anytime, so we want to simplify this complex fraction, and the way we'll do that is by multiplying each individual term by the LCD of all the terms. And sometimes people find it helpful to put everything over 1, so everybody's a fraction. We identify the LCD to be 2, so everybody's going to get multiplied by 2. This becomes the square root of 2 plus the square root of 3 all over 4. When you have a fraction underneath of a square root, you can break it up into the square root of the numerator and the square root of the denominator. So we want to do that. We get the square root of 2 plus the square root of 3 over the square root of 4. And the square roots are perfect. We end up with a final answer of the square root of 2 plus the square root of 3 all over 2. Yes, you can have a square root underneath of a square root. Pretty much every single time with these half angle formulas, you're going to do that simplification of multiplying through by the LCD. And it should be, I can't even think of a time where the LCD is not going to be 2, because if you think about the values that we take off the unit circle, they all have a denominator of 2. Questions at all? All right, let's try another one. I see 22.5, definitely not on the unit circle, but if I double that, 45 is. So that tells me this is half of an angle already on the unit circle, so I know to use a half angle formula. This is the same as cosine of 45 degrees divided by 2. 45 degrees is going to be the alpha I plug into the formula. We want to decide whether we want the plus or the minus from the formula at 22.5 degrees. Is cosine positive or negative?
Positive?
Positive, because we're in quadrant 1. So we know that we'll be using the plus from the formula. This becomes the square root of 1 plus cosine of 45 degrees, all divided by 2. Cosine of 45 is a value we know from the unit circle. It becomes the square root of 1 plus the square root of 2 over 2, all over 2. We want to simplify the complex fraction. We'll multiply each individual term by the LCD of all the terms. Our LCD again is 2. We get the square root of 2 plus the square root of 2 all over 4. And again, we want to break it up into the square root of the numerator over the square root of the denominator and simplify that perfect in the denominator. We get the square root of 2 plus the square root of 2 all over 2. Questions, anybody? And lastly, we have a tangent. Although 3 pi over 8 is not on the unit circle, 3 pi over 4 is, so we can rewrite this as 3 pi over 4 over 2. And this will be our alpha. You can choose any of the 3 formulas you like. Like I said, I usually like to do the last one where we just have sine in the denominator. If you use one of the 2 equations that doesn't have the square root, you don't have to deal with deciding whether it's going to be positive or negative, because it'll just spit out that answer. So depending, if you're comparing with a classmate or something, depending on which formula you use, your answer could look different, but the decimal approximation will be the same. All right, so I'm going to use 1 minus cosine alpha over sine alpha. 1 minus cosine of 3 pi over 4 over sine of 3 pi over 4. Cosine of 3 pi over 4, that's our 45-degree reference angle in the second quadrant. So cosine is negative over there, minus a negative, square root of 2 over 2. And sine is positive there in the second quadrant, so we're going to have positive square root of 2 over 2 in the denominator. Our numerator becomes plus. We have a complex fraction that we want to simplify. We'll multiply everybody by 2. That's going to give us 2 plus the square root of 2 all over 2. If our denominator was really complicated, if it was something like square root of 2 over 3, I would be fine with you not rationalizing that. But since it's just square root of 2 in the denominator, let's rationalize it. It's going to be 2 square root of 2 plus the square root of 4 over the square root of 4. which is 2 square root of 2 plus 2 all over 2. Breaking that up into two separate fractions, we'll get 2 square root of 2 over 2 plus 2 over 2. For a final answer, square root of 2 plus 1. Questions, anybody? In our last example in this group, we're being asked to simplify 1 minus cosine of 5 alpha over sine of 5 alpha. If you look, we recognize this to be the formula that we just used for tangent. It's the right side of the third tangent half angle formula. So this becomes tangent of half of that alpha, and the alpha is 5 alpha over, or just 5 alpha. So this becomes tangent of 5 alpha over 2, and that's it. There's going to be times later in like calculus, or even if we're solving equations in this class, that something like tangent of 5 alpha over 2 is going to be much easier to deal with than that fraction 1 minus cosine of 5 alpha over sine alpha. So sometimes we want to make this switch. Questions at all on half angle formulas? Okay. Next up is power reducing formulas. So for whatever reason, I don't know, it's like students gravitate to power reducing formula, that every time they see sine squared, they're like, oh, power reducing formula. Please do not gravitate immediately when you see sine or cosine squared to a power reducing formula. 9 times out of 10, when we are solving an equation or proving an identity or something like that, and we come across sine squared or cosine squared, 9 times out of 10, we are going to be using the Pythagorean identity, not a power reducing formula. So I just, want to throw that out there. Remember, sine squared plus cosine squared equals 1. So a lot of times we'll manipulate this and replace sine squared with 1 minus cosine squared, or replace cosine squared with 1 minus sine squared. So just heads up on that. This should not be your like instinctual go-to every time you see something squared. You're going to use this much more in the calculus sequence than you are in this course or even in pre-calc. But we still need to know how to use these formulas, so we're going to practice doing that. We want to rewrite as an equivalent expression that does not contain powers of trig functions greater than 1. All right, so 10 cosine to the 4th. Our power reducing formulas are only for squareds. So we need to manipulate this into something squared. This is the same as 10 times cosine squared squared. We'll use our power reducing formula for this part here in the middle. And our power reducing formula is 1 plus cosine of 2 theta all over 2. We want to rewrite this so we only have powers of 1, but I still have that exponent of 2 on the outside, so we need to deal with that. How do you think we're going to deal with that?
Distribute it.
Just like square each thing individually?
Yes.
So it's
No.
super tempting to do that, but the problem is this plus sign in the numerator. Now we can square the top and square the bottom, and just get 4 on the bottom, but we have, like I said, this plus sign, so this is a binomial squared. We're going to have to write this twice and FOIL it out. But I can square that 4 on the bottom. We can simplify the 10 and the 4. Right, 2 goes into both of these. But then we'll have to FOIL that stuff in the top. It's going to be 1 plus cosine 2 theta plus another cosine 2 theta plus cosine squared 2 theta all over 2. We have like terms here in the middle that we can combine. Five times 1 plus 2 cosine theta. Oh, sorry, it's 2 theta there. Plus cosine squared 2 theta all over 2. Questions on anything so far? Well, we've done all that, but now that we've cleaned it up as much as we can, we are still left with a power greater than 1. So we need to repeat the application of our power reducing formula, and we are going to substitute 1 plus cosine 2 theta over 2 in for that portion. Yeah, I think I'm just going to put 5 halves out in front instead of writing a big fraction. This becomes 1 plus 2 cosine of 2 theta plus the fraction 1 plus cosine of 2 theta. Now, careful here. Our theta is the 2 theta. So the formula says multiply your argument by 2 when you do the power reducing formula. So our argument is going to become 4 theta. And then over 2. And now we just want to simplify it as best we can. I think I'm going to break this fraction up into 2. 5 halves times the quantity, 1 plus 2 cosine 2 theta plus a half plus cosine 4 theta over 2. We've got some like terms here that we can combine. That's 5 halves times 3 halves plus 2 cosine 2 theta plus cosine 4 theta over 2. And then last but not least, we want to distribute the 5 halves in. Going to give us a grand final answer of 15/4 plus 5 cosine. Oh, I magically turned the x into a theta, I see, from the get-go. Okay, sorry about that. All right, cosine of 2 theta plus 5/4 cosine of 4 theta. And there we go. when we're in Calc 2 and we're integrating something like this is going to be way easier to deal with than that 10 cosine to the 4th. Questions at all? I don't think any of it's like particularly super difficult. It's just, you know, you really got to take your time because there are little places that you could possibly make mistakes. Let's try another one. 8 sine squared cosine squared. So we'll have the 8 out in front. We'll use our sine power reducing formula and our cosine power reducing formula. It's going to be 8 times 1 minus cosine 2 theta over 2 times 1 plus cosine 2 theta. Dang it, I keep switching to theta. Sorry, x's. Busy looking at the formula and not the problem. There we go. All right, so very similar to the previous example, we're going to multiply the numerators together and multiply the denominators together. So maybe a rewrite would be helpful before you actually started multiplying. That's up to you. Foiling our top, and I'm also going to simplify the 8 and the 4. I guess I'll do that first. So we just have a 2 out in front, and then when we FOIL, we're going to have 1 plus cosine 2x minus cosine 2x minus cosine squared of 2x we have like terms here in the middle that when we combine are going to fall out. So that leaves us with 2 times 1 minus cosine squared of 2x we have a cosine squared left. So we're going to have to apply our power reducing formula a second time. This is 2 times 1 minus 1 plus cosine, and now it's cosine of 2 theta, and our theta is already 2x, so this is going to become 4x all over 2. Just like in the last example, I'd be inclined to break this up into 2 separate fractions. 1/2, and then cosine of 4x over 2. Now be careful here. See what happened? We are subtracting this whole thing. So this negative gets distributed to each. So my cosine became minus because we need to distribute that in. I feel like those are the little things that kind of get us in these types of problems more so than the trigonometry. It's just little algebra things. 2 on the outside, 1 minus 1/2 is a 1/2 minus cosine of 4x over 2. And then we'll distribute our 2. 2 times a 1/2 is 1. Next, the 2 in the denominator are going to cancel, minus cosine of 4x. So there we go. 1 minus cosine of 4x. Questions, anybody? So that is all the formulas that we are going to be learning in this course. And now we're going to actually start doing something with these formulas. Although, you know, I want to look at the calendar. I feel like maybe that's all we're supposed to be doing this week. I mean, we can keep going if you want. Some of my other classes are just like, yeah, just keep plowing through. But I feel like next week, the whole week is dedicated to solving verifying trig identities. Yeah, so it's up to you. If you guys want, I can keep going with verifying trig identities. If not, we can stop here, or I can just kind of field any general questions. You guys let me know.
Good with stopping.
I'm good with stopping here.
Does anyone object to stopping? Any objections at all?
Like, we could keep going, but I mean, if everyone wants to stop, we can.
Yeah, I mean, verifying trig identities next week. I'm definitely going to get through all that, no problem.
The real question I have is, do we have homework based off of this?
Well, sure. Your My Math Lab homework's always rolling,
Okay.
right? And you have a take-home quiz that's posted that isn't due. I felt like we made a decision last time, and I scribbled it on a piece of paper and didn't actually do it. Maybe it's like the first.
I have it
Oh
written.
no, not even. Geez, the 6th or 8th. So the first take-home quiz I'm going to make due on the 8th. The
Oh, which
chapter
take-home
5
quiz is
take-home
that?
quiz.
Chapter 5.
Yeah, you had said the 8th before for the take-home quiz,
Yeah.
and then the next one would be the 13th.
Yeah, there you go. So that's scribbled on some piece of paper somewhere. I'll write it again. So, I mean, it's just kind of keeping up with your My Math Lab homework.
All right.
All the due dates are posted there. So, anybody have anything else that they want to talk about? All right, well, then have a wonderful weekend. If anybody didn't complete the survey about office hours, please do that as soon as, like right now, because today I'm going to decide when all my office hours are going to be and get those posted. So I'll have them posted online. I'll also send you an email, I'm sure, with that information. If you need anything, please let me know. Otherwise, have a great weekend, and I will see you on Tuesday.
Thank
You
you.
too,
Have a good
Mr.
one.
Kraft.
Oh, and everybody should have got their scanned, emailed copy of their exam. So if there were any
Yes.
issues with that, please let me know.
Yes, thank you, Mrs. Kraft.
I am not going to send you your quizzes because scanning that was a real pain in the butt. Okay. All right. Have a great weekend, everybody.
You
Yeah.
too.